My name is Ari Berestiano. I'm from the economics department in the social sciences. And today I'm going to talk about Minkowski summation, okay, this operation on sets. I'm going to start by defining the terms, giving some background, and then we'll go over some basic properties of this operation and see how it fits or how it relates to operations on vector spaces that you might have heard about before. So first of all, let's start with the basic concepts and the environment in which this summation is defined. We'll talk about vector space, which is the RK, the real line k-dimensional. And the distance that we will use is the Euclidean distance. Okay? Some of the terms can be generalized to more abstract spaces, but we will stay with the simple one. Okay, so in this space, we know that we can take two elements of RK, A and B, and sum them. This is well defined. And we also can take just a constant, lambda, okay, and multiply it times a vector A. So those basic operations, we know them. So now think about two sets, okay, subsets, A and B, both of them subsets of RK. Okay? And we want to define a summation when what happens if we sum two sets in RK. So we define, okay, so this is the definition, A, and we will use a special sign for the plus because it's not the same summation like two vectors, A plus B, okay, is the set of all A plus B such that A is in A, capital A, and B is in capital B. Okay, so that's the definition of Minkowski summation, and we use this special notation for the summation just to separate it from this summation, which is sum between two vectors. Okay, so also on sets, another operation that we will need is the lambda. Okay, what if we take a constant, a number lambda in R, and we multiply it times set A, again, A subset of RK, that's similarly going to be lambda times A, such that A, small a, is in capital A. That's also very simple. Okay? So this is the Minkowski summation and the definition, and we will now look at this definition and try to see what properties, what kind of things can we say that are true for the Minkowski summation. Okay? So let's start with very simple properties, okay, for the Minkowski summation. And the first one is commutative. Okay, so it's commutative in a sense that A plus B, the Minkowski summation of A plus B, is the same as B plus A. Okay, so as it works for two numbers in RK, it works for two sets with the Minkowski summation. So that's good. That's the first property that we want to write. The second property that we want to have, which is also true, is that if we take three sets, okay, A plus B plus C, okay, and we first take the sum of the first two, and then we add the third one, it will be the same as first summing the last two. Okay, this is special summation, Minkowski. Okay, and then adding the first element. Great, we like that as well. Going back to this constant, lambda time A Minkowski sum B will be equal, or is equal, to A time, or lambda time A, Minkowski sum lambda time B. Okay, so all these three as expected, and it's good that they are correct. Number 4, okay, let's take the set that contains the number 0, the vector 0 in Rk. Okay, so if we take A, Minkowski summation, a set that contains only one element, the number or the vector 0, as expected by the definition, we'll get A back. Okay, so we are very happy that we have these 4 basic properties. Otherwise, let's admit it, the concept or the Minkowski summation wouldn't make a lot of sense. Okay, so these are 4 very basic properties related to the definition of the Minkowski sum. In the next video, in the second video, I'm going to talk about a little bit more interesting, a little bit more complicated properties of the Minkowski sum that it may satisfy or perhaps does not satisfy. Thank you for watching.